In this video chapter, we're going to introduce the multiple probabilistic trend family modeling framework. This modeling framework has many applications. First of all, it would apply to multiple lines of business. The relationship between multiple lines so that you can design what's called a composite model for a composite triangle group, composite triangles comprising the various lines of business, and also then write one company-wide report. In that composite model, you'll see there are two types of correlations, so what are called process correlation, and there's also parameter correlation. The MPTF framework also applies to multiple segments, such as medical versus indemnity, same line of business, different states, gross versus not of reinsurance data. You'll see that gross data is highly correlated to specifically process correlations vary to net of reinsurance data, and by designing a composite model for these two triangles, you can also find out very quickly whether the current outgoing reinsurance program is capital efficient. And that is the coefficient of variation of net reserves less than the coefficient of variation of gross reserves. MPTF also has major applications to layers, also to pricing, high severity, low frequency data. It also has applications to credibility modeling, and that is when you only have a few years of data available, and as a result of that, you don't have credible estimates of certain parameters. For instance, the triangle might be very small in terms of the number of accident years, and as a result of that, you can't measure the development out here in the tail. Perhaps also as the relative process variability is high, you don't have a significant or credible estimate of the inflation. The IOTA along the calendar years, if there's another piece of business, it might be industry, same line of business, perhaps written in a different state, where you have a larger triangle, then you can design a credibility or part of a composite model for this triangle here, using the data there. And we'll be showing you some examples of this. Another example of credibility modeling is you already have a triangle of reasonable size, but as a result of a lot of process variability, it is hard to estimate the calendar year inflation. I mean, you can estimate it, but it's subject to a lot of uncertainty, or the estimate is not credible. And again, by using related information, you're pulling strength, and you'll adjust in a kind of scientific credibility framework certain parameters. But only those parameters which are significantly non-different to the ones in, say, the industry or another triangle, another piece of business. Another major application is breaking up a triangle into two pieces. So you've got one piece of business, and it turns out that the mix of risk might change from this accident year to the next accident year, and therefore you believe that the development here might not be the same as the development there, that the inflation here for these calendar years might not be the same as the inflation for these calendar years. So you break it up into two triangles that add up to the original triangle, where you have data here, but in this triangle the corresponding accident years are all filled with zeros, or they're missing, and over here you have zeros, and this is the data for the bottom part of the triangle, so you'll be measuring as disinflation the same as disinflation. You would design a composite or composite model for the two triangles, and using that composite model, you'll find the distribution of aggregate reserves for the two, which is the distribution for this particular triangle. It gives you really a lot of flexibility, so it might be due to a change of mix of business. This development is not the same as that. That inflation is not the same inflation. Development patterns might not be the same. And the other thing is that the process variability here, because you might be running a much larger volume, could be different to the process variability there. So that's another reason for breaking up a triangle. What are the advantages of and the benefits, major benefits of the MPTF module, the Multiple Probabilistic Trend Family Modeling Framework? Well, level of diversification between lines of business, so you can assign capital optimally to each line of business using a covariance formula, but that covariance, I must stress, is measured from the data. Mergers and acquisitions, if you're writing these many accident years for a particular line of business in a particular territory, the company that you're buying writes the same line of business, but obviously not necessarily the same mix of risks. Instead of aggregating the two triangles, you can model them and create a composite model and that relates the two triangles, and it might turn out again the disinflation here is not the same as the inflation in the larger triangle. There's no need to add the two up. When you write a new business, you are a reinsurer, you're writing new business, the cedent wants to place some business with you. Well, the first thing I think you need to find out, how's the business that you're just about to write related to everything that is already on your book? So let's look at a very simple example where two lines of business are related. And I've called these lines of business LOB1 and LOB3. And if I open them both and I run the model for each, one of them has a model called good 3, one of them has a model called good 1. And if we look at the model display, just versus calendar years, you will notice that each line has a new calendar year trend starting in the year 2000. This one is 11.42% plus minus 3.3. This is 7.9% plus minus 3.23. If you now look at the residuals, let's close the model displays. If you look at the residuals carefully, let's look at the left starting in 1998. The residual pattern seems to be going down, decreasing up to 2000, then going up, then flattening from 2002 and 2003. On the right is a similar picture. 98 to 2000 is down, 2000 to 2002 is up, and then down. Okay, if we close the two triangle groups, we can create a composite. I'd like to say a composite, create a composite TG. Let's call it LOB1, LOB3, 19, I'll just give it a date, 02, 2007. So you'll see there's a new composite TG here. Let's open it. If you look at the composite data set, there's one by default, but it includes all the incremental paid loss triangles in both triangle groups. So let's remove these from the composite data set. Now we have a composite data set that contains the paid loss triangle from each triangle group. The triangle groups are LOB1, LOB3. All really a composite triangle group is a link to its members, its basic triangle groups. So it's a link to LOB1 and LOB3. I can access LOB1 or LOB3 either through the database or through the composite. There you are. If I go back to models for my composite DS default data set, a composite data set is not an aggregate. It's just the two triangles sitting side by side or one below the other. If I go to models, there aren't any composite models, but they're related models, so let's run them, good 1 and good 3. And if we run these two models now, we're actually using the correlations and the residuals. Let's find out what they are. Here are correlations. We're using these correlations to estimate the parameters. If I look at this residual graph for LOB1 and compare it with LOB3, LOB1 versus LOB3, if I export the residuals by accident year and development year as one column, these residuals and these ones into Excel and calculate the correlation is 0.352. And that correlation was actually used to estimate the parameters in each of the models. If I instead, if I were to set the correlations to 0, I can do that. These estimates will be the same as the estimates we had in the probabilistic trend family. For each triangle, I've got its own independent model. Now let's use the correlations. So the estimates will change a little bit. Okay. So what have we done? We've got one model, we've got another model, but now these are the correlations and these are the two sets of residuals that are correlated. So we have one model, we have another model. Each model on the log scale is a linear model. Each one has its own set of parameters. But now the correlations, there are correlations between these residuals. So you can actually stack up the two observation vectors on top of each other, and then when you use generalized least squares to estimate these two parameters, the correlations in these residuals feature in the estimates. In fact, you need to calculate the parameters of the model, the grand linear model, recursively, because you calculate the correlations and the residuals. We estimate the parameters using the correlations. You then get new estimates for the correlations, use those correlations again to estimate the parameters. So the grand model looks like this, and the covariance, variance, covariance matrix are no longer diagonal. Okay, well, we've done that. Now, the fact that these two sets of residuals are correlated, we call that process correlation. And what do we mean by correlation? So let's study correlation a little bit. And I'm going to stress right at the outset that linearity, correlation, weighted least squares, normality, and regression, weighted regression, are all the same concepts. So what do we mean by the following linear model? You have two random variables, x and y. Well, let's draw a picture. Let's suppose that x is height, ht, and y is weight, wt. So you take a subpopulation of people that have a height somewhere, say, between 170 and 171 centimeters, and you then draw a frequency plot of their weights, and it's normally distributed with a particular mean. You then take another subpopulation. For this particular subpopulation, the height might be, say, 180 to 181 centimeters, and for this subpopulation, you also draw a frequency plot for the distribution of weights, and it's also normally distributed, but the mean is higher. And you do it for this intermediate height values also. And what you find out is all these normal distributions have the same variance, but you can actually also connect the means by a straight line. So this is the property that applies to what's called a bivariate normal distribution. So if you have two random variables x and y, if they have a bivariate normal distribution, the mean of y given x is linear in x, which we found, say, by doing this hypothetical study. The variance of y given x is a constant. It doesn't depend on x. Now, of course, you would also say that the distribution of y given x is normal with mean alpha plus beta x and this constant variance here. The slope of the line beta is related to the correlation between y and x, so it equals the correlation multiplied by the standard deviation of y divided by the standard deviation of x. And correlation in statistics is a definition. This is the way correlation is defined. It's the covariance divided by the standard deviation of each variable. Now, if the correlation equals 0, then the slope of the line is 0, and vice versa. If the slope of the line is 0, then the correlation equals 0. So here's a question. This is why, before the question, this is why in the usual linear model, y equals alpha plus beta x, where the expectation of y is alpha plus beta x, the variance of y, which is the same as the variance of the error term, it's independent on x, just a constant. Now, if you have a random variable t that has a normal distribution, say with mean 0 and variance 1, and s equals t squared, then s is a function of t. It's related to t. It's a quadratic in t. What's the correlation between s and t? Now, most people, their gut feeling would be that the correlation is 1. No, the correlation is actually 0, because correlation, the statistical definition of correlation, is linear association. You might remember that I said early on that correlation, linearity, weighted least squares, multivariate normal, weighted regression are all the same concepts. In fact, the only time the correlation between two random variables equals 1, correlation between two random variables equals 1 or plus or minus 1, is if and only if you can find two constants, say alpha and beta, so that you can write one as a linear function of the other. In this particular case here, where t is normal 0, 1, and s equals t squared, the covariance in fact is 0. I guess you could also argue that quadratic is very far away from a straight line. Okay, so this is very important. In ICFS here, for these two models, each set of residuals has a normal distribution. So the correlation is the linear association. It's the linear correlation, and it's, in this case, 0.352. Now, what does that mean? That means, let's see, if you had the two lines being independent, well, we always know that the probability that a residual is positive, the outcome is above the trend line, is 50%. The probability that is below the trend line is also 50%. But given now that the two lines of business are actually correlated, there's process correlation, we're now actually saying that if in one line in a particular cell the residual is positive, in other words, the outcome is above the trend line, in the other particular line of business, the probability that is above the trend line is no longer 50%. It's going to be higher than 50% because of the linear correlation. Now, of course, if the correlation was close to 1, the probability then will be almost 1. If in one cell the observation is above the trend line, it's very likely to be above the trend line in the other line of business. Okay, now if we look at these two parameters here, if we forecast for this particular line of business going forward, we'd assume that the actual trend comes from a normal distribution with mean 8% and standard deviation 2.94%. In the other line of business, we'd assume that it's coming from this normal distribution. However, if you optimize across the line of business, we actually now find out that the true trends are the same. So let's save that model as the optimal model. There's no statistical evidence that the trend in either line is different. And this is kind of the worst kind of correlation you can have now. But before, one thing I forgot to show you, if we estimate the parameters on their own, you'll see that they're correlated. There is parameter correlation. Now, what does that mean? That means that if in one line of business, the actual true trend, say, is larger than 11.612%, the probability that is also larger than its mean in the other line of business is no longer 50%. It's going to be more than 50% because these two trends going forward are correlated. Okay, let's optimize again, and now the correlation will have to be 1 because the two parameters are the same. If I now forecast going forward for the aggregate of the two lines, what have we done now? Let's go to the PowerPoint display. You know, when you forecast for one line of business, for the model for one line, ICFS will produce log normals in each cell which are correlated, different log normals, and they're correlated. Here, we're producing log normals for each line of business, but now the correlations are not just within triangles, but you've got correlations between triangles. Now, these correlations between all the cells which are induced by the parameter correlation And the process correlation also induced correlations between the accident years, these accident years, and these accident years, these calendar years, and these corresponding calendar years, and the distribution of the aggregate reserve for that line and the distribution for the aggregate reserve of that line. So we've just done that, and because we have positive correlations, in the aggregate table, the variance of a sum will be larger than the sum of the two variances. Let's go to forecast summary, let's go to the aggregate, and let's look at correlations. So the correlation between the two reserve distributions, one reserve distribution is has a mean of 697.5 million with a standard deviation of 90.6 thousand. Million, units are in thousands. The other distribution has a mean of 1.13 billion with a standard deviation of 143 million, and the correlation between these two distributions is 0.02. On the log scale, the correlation will be a little bit higher. If you allocate capital based on the covariance formula, and for the aggregate of the two lines, so you want to set capital at the 95th percentile, then 37% of the risk capital that's above the mean will be assigned or allocated to LOB1, and 62% should be allocated to LOB3. So you've got forecast summaries for each line of business, comparisons, summary graphs. For each line of business, you've also got correlations between the accident years reserves, calendar year reserves. Of course, you also have this for the aggregate. You've got correlations based on the totals by accident years, calendar years. Well, there's a lot of information just in this one particular display that has lots of tabs in it. If I want to find the distribution of the aggregate, which is the distributions, if you go look at the forecast table, the aggregate by calendar years and accident years, we do a simulation from the future cells for each line, and of course we can save this to a file where if we give the file a name, one name, you'll have extensions for the aggregate and for each line. So for the aggregate and for each line of business, you'll have a separate flat file, a text file that has all the simulated values by calendar years, accident years, and the aggregate. In fact, if you really wanted to, you could also store simulated values as sent to a file for every cell. Anyway, we're not going to do that, but it's very easily done. So this is now the 10,000 values that we simulated by accident year for the aggregate of the two lines of business. You can also look at it by calendar year. And you can also look at, say, the quantiles, percentiles. We've done this before with 1M, 1M excess, 1M, and 2M. If we want to find the, look at the percentiles or quantiles in descending order, the 95th percentile is 2.231 billion. The value at risk at 95% is 390 million. And this is for the aggregate, where you don't really have that much diversification because you've got quite a bit of correlation. Of course, what you could also do is you could go back and estimate the model for the two lines of business, set the correlation, say, to 0. You could do that. And now when you do the forecasting, you're just finding the aggregate distribution as if they were independent. You can also find the distribution of the aggregate by doing a simulation from all the correlated log normals, and then ask yourself how much risk capital do you need at the 95th percentile, and you'll find out that it's less. Because now you've got complete diversification. So then you can actually calculate what additional capital do I need because of lack of this diversification. Before I just finish this particular video, let's just look at, again, at correlations. And I just want to mention that correlations between normals is not the same as correlation between log normals. So there's a lot of misunderstanding. There's a discussion of this misconception on our website. But let me just illustrate. what you could do yourself is simulate from two normals that are correlated. So without loss of generality, you could assume that the mean of each normal is 0. So we've got three parameters: the standard deviation of one, the standard deviation of the other log normal, and their correlation. And of course, you know that as you change the standard deviation of a normal, you don't change the mean of the normal because it's got a separate parameter, but you do change the mean of the corresponding log normal if you exponentiate the normal variable. I guess the same thing applies when you've got two normal random variables that have a correlation of rho, a linear correlation of rho. If you change the standard deviations of the normals, the correlations between the log normals changes. And here's just an example by way of simulation, which you can replicate in your spreadsheet. The correlation here has been set to 0.78. This is the graph of the simulated values e to the y and e to the x, and you can see that by setting the standard deviation of the corresponding normals to be 0.1, that's the correlation between the two log normals. Of course, if you increase the standard deviations of the normals, you don't increase or change the correlation of the normals, but you do change the correlation of the log normals. In fact, you get to this stage and it doesn't even look linear. Well, it isn't. And this is another example. So you've got to be very careful that when you're using another product, with Equifax, everything's set out for you. You make certain assumptions, but all those assumptions are driven and tested using the data. The correlations we calculated here were based on the data, both process correlation and parameter correlation, and we had to test that, in fact, the residuals were normally distributed. So here's an example. You've got two normals. That's their correlation. They look very linear, but that's what the two log normals look like. So be careful when you use a DFA product and it asks you for correlations. What correlations is it actually asking you, and what calculations is it really doing? But again, I want to remind you that in Equifax, you are measuring correlations from the data